In the third portion of the solutions, we will talk about what's called colligative properties. And colligative properties are properties of solutions, not of the pure solvent. So the solutions which show a colligative properties are of course not as the pure solvents. Okay, so solution will behave differently than a pure solvent will. So the number of solute particles that you have in a solution will change the boiling point and freezing point of substances. It may change some other things also. Of course, you know of electrolytes. Okay, so if you have some solute dissolved in any kind of a solvent, then you may or may not have an electrolyte. So that depends on what kind of a solute you have in there. So electrical conductivity will change also. But in this portion, we will talk more about changes in boiling points and freezing point. So there are two kinds of solutes that you can dissolve in a solvent. One is a volatile, one is a non-volatile solute. A volatile solute means that something is evaporating all the time, vaporizing all the time, and a non-volatile solute would be something that is not vaporizing all the time. So for example, a compound like hexane, benzene, these will be considered as volatile because they're always vaporizing. Why are they vaporizing? Because they have a low boiling point. So they'll always be vaporizing. Non-volatile solutes will be like the ionic compound, sodium chloride, potassium bromide, sodium hydroxide. All of these are considered to be non-volatile solutes because they don't evaporate. Okay, they don't evaporate because they have very high boiling points. So you have the volatile and non-volatile kind of solutes, and of course both of them behave differently, which is why we're talking about this. So the colligative properties are actually given by what we call Raoult's law. And with Raoult's law, you can calculate how much the boiling point or freezing point is going to change. Okay, so in general, vapor pressure of any substance will be lowered if a solute is non-volatile. Okay, and non-volatile, remember again, ionic substances. Even substances like sugar, for example, they have very high boiling points, so they're considered to be non-volatile. So the vapor pressure of a solution will be lowered if the solute is non-volatile. Okay, and so this is the formula that is given for calculation of the new vapor pressure of any substance, of any solution. So here is the P1 is the vapor pressure of the new solution. This X1 over here, remember this is going to be the mole fraction. So this is the mole fraction of the solvent that is present, and then P1O, this O. This means that this is the vapor pressure of the original solvent. Okay, so the X1 here, this is the mole fraction. The mole fraction of the solvent will be different if you have a solute dissolved in it. Okay, and that's why we deal with mole fractions to figure out colligative properties. So again, this is the new vapor pressure, this is the original vapor pressure, and this is the mole fraction of the solvent. And then if you have a volatile solute, okay, so there are two kinds of solutes. Remember, volatile and non-volatile. So non-volatile is this way, but if you have a volatile solute, in that case, the vapor pressure will be the addition of the vapor pressure of the solute and the solvent, because the solute is also evaporating, which means it's also exerting its own vapor pressure. The solvent is also exerting its own vapor pressure. So both of them are exerting their own vapor pressure. So which means you need to find the mole fraction of both the solvent and the solute. And once you find that, you need to add those vapor pressures up. Okay, so those are going to be a little bit different than what you would do for a non-volatile solute. So these are the two formulas that you would need. So let's do an example of calculating vapor pressure of a substance, of a solution. So calculate the vapor pressure of a solution made by dissolving 115 grams of urea in a non-volatile, it's a non-volatile solute, and the molar mass is given, so that will save us some time, in 485 grams of water. Okay, so of course you need the grams and the grams because you need to calculate mole fractions. Okay, because you cannot do vapor pressure calculations without calculating mole fractions. So here is our formula. The original pressure of water is given at 25 degrees centigrade, which is 23.8 millimeters of mercury. So this is the formula we're going to use to find the mole fraction of water. We need to find the moles of both of the solute and the solvent. And once we find the moles of both, we are going to find the mole fraction of the solvent, which is water here. So anyhow, moles of water is given by 485 grams of water and then divided by the molar mass. Same thing goes for urea. So now we're going to take the mole fraction of the water, which is 26.91 moles, divided by the sum of both of the moles, okay, of the solute and the solvent. So now you can see, looking at the mole fraction, that the vapor pressure contributed by water is not 1. 1 would be if it was completely all water, okay? But because it's not 1, it is less than 1. The vapor pressure is also going to be less than what it is supposed to be. So once you multiply 23.8 by the mole fraction of water, you'll get this mu vapor pressure, which is caused by the 115 grams of urea in there. So you can see that the vapor pressure is slightly lowered, okay? And these vapor pressures are very important as far as determining the properties of solutions is concerned. So you can actually make something exactly how you want it to be, okay, by getting the right mole fractions. So anyhow, this is a very simple calculation regarding vapor pressure changes. So I said in the beginning to you that there are two changes that will happen when you have a solute dissolved in a solvent, or actually three things. The vapor pressure will change. With the vapor pressure changing, you will have a change in the boiling point also. So they're kind of related to each other. And then the freezing point, okay, that will also change. So let's look at the first one here, boiling point elevation. And the boiling point of any solvent will be raised if a non-volatile solute is dissolved in it. Now, all of this has to be non-volatile because remember the vapor pressure of a volatile solute is going to be different. Okay, and so in these cases, when we talk about boiling point elevation, it's a non-volatile solute. So here is a graph, okay, showing that thing over here, that principle. The solid red line is the original vapor pressure boiling point, okay, of say water. And then the dash line here is if you have a solute dissolved in it. Okay, so if you have a solute dissolved in it, look at this. The boiling point, okay, originally is here, but when you dissolve something in it, the boiling point will change. It will actually increase, okay? And that is a property of solutions. There is nothing much you can do about it, okay? And so anyhow, boiling point elevation will be directly proportional to the molar concentration. Molar concentration, remember, is moles of solute over kilograms of solvent, okay? That is what it is. So we're working in moles, okay, in this case, and delta TB is the change in the temperature of the boiling point. Kb is a molar boiling point elevation constant, which means it's a constant for every solvent that we use. Okay, so that is how you would calculate the change in the boiling point. Okay, you're not calculating the actual boiling point. Once you have the change of the boiling point, then you will figure out the actual boiling point, all right, from it by adding the difference of the temperature. Freezing point depression is also the same way, which means that if you have a solute, then the freezing point will depress. It will not go higher, so it'll actually depress. So the boiling point goes higher and the freezing point is lower, okay, which is again represented by this dash line here. So water is supposed to freeze at 0, but if there is something dissolved in it, it's going to be below 0. Again, freezing point lowering is going to be directly proportional to molar concentration. It's the same formula, except now that we are using freezing point, so we'll be using Kf instead of Kb, and Kf is the molar freezing point depression constant. Okay, again, these are constant values which have to be given to you of different solvents. Here are some of the constants that you will find for very common solvents. So water, for example, benzene, ethanol, acetic acid, and cyclohexane. These are some of the common solvents that are used in chemistry. And so their normal boiling points are given over here. The Kb constant, the normal freezing point, and Kf is given. Okay, and look at the units of Kb and Kf. They're both degrees Celsius over molality. Okay, and so because remember in our formula we have molality as well. Okay, so that's how you find out the change in the temperature. So let's do an example. Of course, nothing is complete without an example. So let's do one, which is calculate the freezing point and boiling point elevation of a solution that has 268 grams of ethylene glycol and 1015 grams of water. Molar masses are given to us, thank God, because then we don't have to worry about calculating those, although it's not hard, but time consuming. And then the Kb and the Kf, okay, have to be even also. Okay, so these problems are, in my opinion, some of the easiest ones, provided you know your units, provided you know your formulas. So they're very easy to do. Okay, so again, since the solute and the solvent is given to us, we need to find the molality. So you find the moles of ethylene glycol, which is 268 grams, divided by 62.07 moles per gram, and then that gives you the moles of ethylene glycol. And then you find the molality, because that's what we need for a formula. Molality is the moles of ethylene glycol divided by the kilograms of solvent, okay, which is water in this case. So the molality then becomes 4.24 molar solution. So when you're trying to calculate the difference in the freezing point, you will go ahead and use the freezing point depression constant, which is 1.86, that is the Kf, and multiply that by the molality, 7.91. Now remember, this is the difference of the temperature. This is not the final temperature, okay? The final temperature is what you're trying to find out. This is the difference of the temperature. So which means the initial minus final will give you then the final temperature, which 0 degrees Celsius is the freezing point of water. So 0 minus the T final will give you, of course, the negative value of 7.91, okay? Which means that if you have 268 grams of ethylene glycol in that much water, the water is now going to freeze at minus 7.91 degrees Celsius instead of 0 degrees Celsius. Now the same thing you can do for boiling point elevation. Now you're going to have to use Kb, because that's the boiling point constant. So you're going to use Kb, and then you will multiply that by the molality. So it's 2.18. And so now the final temperature is actually going to be 100 degrees Celsius, okay, because that is the boiling point of water. And so then your temperature at which the water is going to boil is 102.18. One of the things to keep in mind, in case you ever forget about these formulas, is that when you have a solute dissolve in a solvent, your freezing point is going to decrease and your boiling point is going to increase. If you keep those two things in mind, then you will always come up with the right numbers, okay, and the right answers. One of the things that you can do with Raoult's law is calculate the molar mass of an unknown substance using freezing point depression or boiling point elevation. So in this problem, we're going to solve the molar mass using freezing point depression. So in a freezing point depression experiment, the molality of a solution of 58.1 milligram mannitol in 5 grams of benzene was determined to be this molar solution, okay, 0.0784. What is the molar mass of anethol? So in this case, the molality of the solution, okay, is given to us. The amount of solute, which is anethol, dissolved in 5 grams is known to us, okay? So we know the quantities, we know the molality. So once we know all of this, then what we're going to do is use the molality to find the moles of the solute. Once we know the moles of the solute, then we can use it to find the mass of the solute, okay? To find the molar mass of the solute. So let's do that over here. So the solute mass is this, and the solvent mass is 5 grams. So solvent we have to convert to kilograms, because that's what molality is. So then we go ahead and calculate the molality of the solution, or excuse me, the molality of the solution is given to us, which is this. And then you find the moles of the solute. So the moles of the solute are going to be 0.078 moles times the amount of solvent. So kilograms cross up with kilograms, and you're left with 3.92 times 10 to the negative 4 moles. Okay, and this is the moles of the solute that are present in here. And once you find the moles, then all you have to do is find the molar mass, which is grams per mole. The grams of the substance is given to us over here. It's given in milligrams, so we're going to have to convert that to grams. Divide that by moles, because that is the unit of molar mass, grams per mole. So then that is going to be our next calculation. So 58.1 times 10 to the power of negative 3 grams divided by the moles that we calculated, and that's 148. So in this case, what is not given to you, as you can see, is how much of the temperature was depressed, okay, with addition of the anethol. So in some cases, which we can we'll do in class also, is you can actually use that data to figure out the molar mass of an unknown substance. So in any case, this is how you would calculate the molar mass using freezing point depression. So in this example, let's look at also the calculation of molar mass, but this is using the boiling point elevation. The previous one was using freezing point depression, where we didn't really use the freezing point depression that much, but here, let's see, this is a different one. So 11.2 grams of sample of sulfur was dissolved in 40 grams of carbon disulfide. The boiling point elevation was found to be 2.63. What is the molar mass of sulfur in the solution? And then what is the formula of the molecular sulfur? So the Kb is given to us for the solvent, which is carbon disulfide. So what's our strategy? Our strategy again is to calculate molality. If you look at the previous problem, the molality was already given to us. We didn't have to calculate that, which is why the difference in the temperature was not given. But in this case, the difference in the temperature is given to us. So we're going to use that to calculate the molality of the solution. We will find the moles of the solute as usual, and then we'll find the molar mass using the grams of the solute, which is given to us over here. So let's set it up. Our formula for use is going to be this one, which is for the boiling point elevation. So fill all the data in here. This is supposed to be B. So molality is then the change in the temperature divided by the boiling point constant. And so this is what we do, and then 1.096 is the molality of the solution. So once you have the molality of the solution, it is moles of solute over kilograms of solvent. So that's nothing new. So what we need to do is find the kilograms of the solvent, which is 40 grams. You just convert it to kilograms. Okay, and so the moles of the solute can then be figured out by multiplying molality times the kilograms of the solvent. So this is what we do, and then the moles of the solute then are 0.044383 moles. And again, remember, don't round off anything. Okay, not in the middle of the calculation, only when you get to the end of it, then we'll round off to 3 sig figs, but not right now. Okay, so continue using about 4 to 5 significant figures. All right, so then the next step would be using the moles to find the molar mass. Okay, and the molar mass is going to be 11.2 grams divided by the moles, so it's grams per mole. That's 255. Now remember, they're talking about sulfur. Okay, now sulfur, if you look at the periodic table, obviously is not 255.5 grams. Okay, then our next question is, what is the formula of the molecular sulfur? So obviously this sulfur is not the same as the sulfur they are talking about, so which means we need to find out more. The empirical formula for sulfur is just S, okay, as given in the periodic table, which the atomic mass is 32. So which means now what we have to do is divide 255 by 32, which gives us approximately 8. So which means that the compound we are talking about, or the sulfur we are talking about, is actually S8, okay, which is probably an allotrope of the sulfur, okay, that we originally have. So anyhow, this is how you would do a calculation if the change in the temperature was given to you. You can do exactly the same calculation if you had freezing point depression. In case of freezing point depression, your constant would be for the freezing point depression, that's all. But everything else is going to be the same way that you do boiling point elevation. Now for one other property that changes with solutions is osmosis. Okay, we have not talked about osmosis yet because it is a property of solutions, and it is osmosis is when you have a movement of the solvent molecules through a semi-permeable membrane. Okay, so when you have just solvent going through from one place to another place, just water, when you have pure water, that's called absorption. Okay, when you have a surface property, it's called adsorption. But when you have specifically from a solution just solvent molecules going through a membrane, that is called osmosis. So it's a very, very specific thing. Okay, keep that in mind. And then there is something called osmotic pressure. Osmotic pressure, which is given by pi, is the pressure that stops osmosis. Okay, and this is an important part, because what if you don't want the solvent to go out? Okay, and so osmotic pressure generally would be a colligative property, because we just saw that vapor pressure is affected by the amount of solute, okay, that you have in there. So this is the formula that we use for osmosis or the osmotic pressure. And because we're talking about osmotic pressure, we have to talk about gas constant over here. So pi is given by mRT, and R is gas constant, M is molarity. Now we're back in molarity, not in molality, molarity, and then T is the temperature. And once we talk about the gas constant, we want to make sure that your temperature is in kelvins now. Okay, so here is a little bit of a visual, okay, looking at what osmosis is, okay, all about. So here are water molecules, and then here's a solution, okay, of glucose and water. Okay, so if this is the glucose solution and here is water, what's going to happen after a while is that these water molecules will start going through this membrane and enter through here into this funnel. And so then you see that after a while, there's more water in the funnel because the water has gone through. Okay, so this is kind of what osmosis is all about. And once equilibrium is reached, then no more water will go through, and that is the osmotic pressure, which is stopping any more osmosis from happening. When you have electrolytes, things are a little bit different. Okay, so you can have solutions that are made up of different kind of substances. Okay, so for example, in the solute case, you can have non-electrolytes like sugar. You can have electrolytes like NaCl, which will ionize to give you 2 ions, and then you can have electrolytes like calcium chloride, which when they dissociate gives you 3 ions in there. Okay, and so osmosis will depend, okay, on how many ions you have in there or how many particles you have in there. So the dissociation of strong and weak electrolytes will affect the number of particles in a solution. If you have something like glucose, which is a non-electrolyte, okay, if it's a non-electrolyte, it means that it is not ionizing. If it is not ionizing, you have only one particle to deal with. But if you have an electrolyte in there, for example, if you have ionic substances in there, then you will have to worry about how much dissociation is occurring, because if the dissociation is good, then you have a strong electrolyte. Then it means you have 2 particles or 3 particles. But if you have a weak electrolyte, then you really don't know how much of ionization is going on unless you do some calculations. So in case of weak electrolytes, you may not have an accurate particle count, okay? So in those cases, things are slightly bit different, and osmosis doesn't quite work the same way. Okay, and so you can find out how much it will affect, the number of particles will affect the osmosis by using the Van 't Hoff factor, which is I, and it accounts for the effect of dissociation. Okay, so for example, I is the actual number of particles in solution after dissociation, and then number of divided by the number of formula units initially dissolved in the solution. Okay, and so for example, if you have NaCl, then NaCl, the formula unit is 1. The actual number of particles will be 2 because NaCl dissociates completely. So 2 over 1, which means that I is going to be 2. If you have something like, say, silver iodide. Now, silver iodide is the number of formula unit is 1. But silver iodide is not very soluble in water, which means that you may not actually have 2 particles in there. You may have 1 particle in there, maybe not even that. So maybe it could be even 1. It could be less than 1. So which means that this I then becomes a fraction. Okay. So it depends on what you're trying to dissolve in there. Okay. And so you have to be careful, okay, when you deal with electrolytes in there. Non-electrolytes, 1, that's it, because non-electrolytes are not dissociating, so I will always be 1 for non-electrolytes. The modified equations that's used for colligative properties for boiling point elevation and freezing point depression, and then also for osmosis, as the year that you add I to it. Okay, so you can see that it is directly proportional, which means that if you have more number of particles, then you will have more of a freezing point depression. If you have more particles, you will have more of a boiling point elevation, which makes sense because that's exactly what colligative properties are. Okay, is that the more amount of solute you have, the more boiling point elevation there would be. So that's how you use the Van 't Hoff factor. Very simple and very easy to use. So here's an example for that calculation. The freezing point depression of a 0.1 molar magnesium sulfate solution is 0.225. Determine the experimental Van 't Hoff factor. So we're going to calculate for I in this case. Okay, so we're talking about freezing point depression. So here's how you can do it. Okay, just one way of doing it. There's another way of doing it, but we'll do it one way here first. So calculate the I directly, okay, which means that you have the delta TF, which is 0.225, and then you have the KF, the freezing point. That would be the freezing point constant of water, because this is magnesium sulfate solution. And remember, if the solvent is not given to you, assume it's water. So here is for water, and then the molality is given to us, which is 0.1 molar. Okay, and so then you can see that I comes out to be 1.21, which is really weird because technically speaking, magnesium sulfate, one formula unit has two ions in it, magnesium and sulfate. So which means I is not exactly 2 over here. So this is also a good way of finding out how much dissociation has actually occurred of your solute, okay, in a solution. The other way to do this, okay, is to find out and compare the different freezing points that you would have. Okay, so for example, in this case where you have a 1 molar solution, you find the change in the freezing point. Okay, for this one. In the first case, we actually use the change of freezing point, but in this case, we're going to find out what freezing point you should actually get. So using the same freezing point constant and multiplying that by the molality, okay, of the solution, you find out that the freezing point is this. Okay, so then this freezing point would be if this was an ideal solution, which means that this should be at the bottom then. Okay, this is what it should be. But the thing is that the data you're getting is 0.225. So this is another way of doing it. You then just divide the two and you still get the same answer. Okay, this one is a little bit easier to do because this is directly giving you the answer. This is a two-step process because you first have to figure out what the ideal freezing point should be for magnesium sulfate. Okay, but then ideally if this is it and this is what you're getting, then obviously it's not the same thing, which means that dissociation is not the same for magnesium sulfate as you were expecting. So anyhow, this is how you can calculate also how much dissociation has occurred. Okay, so this example is to deal with osmotic pressure, but now we're going to calculate the molar mass of an unknown substance using osmotic pressure. So previously we've done it with boiling point, elevation, freezing point, but we can also use osmotic pressure for this. So here's the problem. A solution made by dissolving 25 milligrams of insulin in 5 milliliters of water has an osmotic pressure of 15.5. Okay, and so the temperature is given to us, which is nice, and then calculate the molar mass of insulin. So then we're also told to assume there is no change in volume. That's an important thing. And then of course that insulin is a non-dissociating solute, which is also good because then we don't have to worry about the Van 't Hoff factor. Okay, and so this is a good thing. If these things are not given to you, you can just assume them. Okay, so don't wait for the question to assume all these things. Assume it yourself. Okay, so what is our strategy? Remember, we are supposed to calculate the molar mass of insulin. To calculate the molar mass of insulin, you need to know the moles of insulin. To know the moles of insulin, you will need the molality or the molarity, okay, of insulin. But because we're dealing with osmotic pressure, we can go with molarity because that's the formula we are going to use, okay? So, but before we get there, I want to make sure that we have everything in the correct units. Okay, so for example, right here, the osmotic pressure, we are given that in millimeters of mercury. We'll convert that to atmosphere, and then we'll convert the temperature into Kelvin. Okay, because the formula we're going to use is going to be this one, which is that osmotic pressure is equal to molarity times the gas constant and the temperature. Okay, so if that's a formula, this is how we'll get the molarity, which means that molarity is equal to pi over RT. And if it's over RT, then here we go. So our osmotic pressure is the atmospheres over here divided by R. R is this, okay, 0.0821, which is back from the gas chapters. And then the temperature, okay. So once you have this, you have the answer of molarity. Molarity then is 8.338 times 10 to the negative 4 moles over liter. Okay, so remember we needed to get moles. Okay, so here's the moles that we need, okay, of our insulin. So now we need to find out the moles exactly, because here is the volume given to us of water. To figure that out, we need to convert the 5 milliliters to liters. That is exactly what we're doing over here. So moles then is equal to molarity divided by liters multiplied by the volume. Okay, so that will give us the moles. Again, if you need for yourself, you can go ahead and cross out the units to make sure that you're in the right units. So for example, liters, liters, milliliters, milliliters, cross out, so you're remaining with moles. So in any case, once you find out the moles of insulin, then what we need to do is calculate the molar mass. For the molar mass is, remember, grams per mole. So this is the milligrams given to us, so we'll convert that into grams. And once that is converted into grams, then you just divide that by moles. So grams per moles will give us the molar mass. So this is the molar mass of insulin. Okay, so it's not that much of a complicated calculation. You just have to make sure you go step by step through all of this, and then make sure you don't round off in the middle. You keep your 4 to 5 significant figures. Your answer should be in 3, okay, but your in between calculations can be 4 to 5 significant figures, and keep going. Okay, just take it step by step. So osmosis, where do you find osmosis? Pretty much everywhere. It is a key transport for blood, and it is also a key transport as far as plants are concerned. They all take up water by osmosis, and blood is the most important application as far as our living body is concerned. So this little slides here, these pictures over here, they are shown for how water and blood cells are related. Okay, so in case when you have, remember our blood itself is made up of a lot of water, which has solutions in it, and then we have a blood cell. Okay, so we have 3 different kinds of solutions: hypertonic, isotonic, and hypotonic. Hyper means when you have something more, hypo meaning when you have something less. Iso means when something is equal. So it means that this is equilibrium, okay, in case of iso. So when you have a cell, okay, and water flows out of the cell, that means that the cell is dehydrating, and that is called crenation, and that's a hypertonic solution. Hypertonic solution meaning if the water is flowing out of it, okay, then you have concentrated solution out here. Okay, so the water is flowing out of the cell. When the water is coming inside, it means that you have more of the water outside. Okay, so the water is actually coming into the cell, and once it flows into the cell, it's called hemolysis. All right, and so these are the situations that happen in case of water transportation and blood. And this is kind of an important thing when drugs are being administered in patients. So they have to make sure that they're going to be isotonic so that you don't kill the cell, okay, or you don't bloat it up, okay, in that case. So the reason that we don't drink seawater is because of this reason, okay, the crenation reason, because if you drink seawater, then the concentration of salt is higher, and so the water molecules will flow out of the cells, okay, and cause the cells to shrivel up, okay, and so seawater is really not that good for drinking. Yeah, the taste is not good either. And then we have a special kind of solution which we call colloid, okay, and the colloids come from a different type of solution. We talked about different solutions before, as in dilute, concentrated, and all that. But here is another classification of solutions, something called a true solution and then colloids. A true solution is a homogeneous solution, okay, and a true solution means that you cannot tell whether you have a solution or not. And a heterogeneous solution would be like a colloid. But then colloids are not exactly heterogeneous solutions. Okay, I mean, there is a difference because colloids are very, very specific in the particles. Okay, the dispersion of the particles is very specific. The particle size is very specific. And then the dispersion usually is very homogeneous in the sense that, you know, the particle size is almost the same. Okay, in case of a colloid, when you just have a heterogeneous solution, then the particle size can be anything, all right? But when you have a colloid, then we're talking about a particle size of a certain size. Okay, so here 10 to the power of 3 times 10 or to the 10 to the power of 6 picometers. So examples of colloids are given to you over here. So aerosols, foam, emulsions, and you saw some of these solutions before also, okay, where you had a solute and a solvent. And so depending on different kinds of solute and solvents, you can create different kinds of colloids. And these colloids actually have very good properties and they are very useful as far as practicals are concerned. So here, you know, there are some examples also given. So for example, a liquid and a gas, it will give you a foam kind of a colloid. We talked about that before also. And that would be whipped cream, for example. How can we live without whipped cream? So thank God for this colloid. Okay, the same thing goes for mayonnaise. Okay, where you have a liquid and a liquid. The two liquids here is going to be water and fat, and that gives you an emulsion. So there's proteins also involved, and so all of that gives you a nice mayonnaise. Now, from a consumer point of view, if you see a mayonnaise that has oil sitting on top of it, you're like, no, I don't want this. This doesn't look good. Okay, and that is because a colloid is supposed to stay that way, okay, which means it's supposed to stay as a heterogeneous mixture, which is homogeneously um, spread out, okay. It should not separate out into things, okay. So a liquid and a solid would be, for example, milk of magnesia, and we all know that in some cases you have to shake before you actually consume that product, okay. So milk of magnesia is like that. Some of the liquid solids are also nail polishes, for example, and in nail polishes also, you have to shake the bottles. And of course, I'm talking to all the guys here, but in any case, okay, for nail polishes also, you have to shake it up because it's the colloid. Okay, so here are some other examples you can go through for colloids. One way of knowing whether you have a colloid or a true solution is Tyndall effect. Okay, and a Tyndall effect is when you have light that can go through a solution. Okay, and if it passes through a solution without you even knowing that there is light passing through the solution, that is a true solution. But if you have a colloid or if you have any particles in there, then a scattering will occur. Okay, so the light particles that are coming through here, those particles will start reflecting those lights, and that light scattering is called Tyndall effect. And so that is how you can tell whether you have a true solution or not. Okay, so sometimes a solution may seem like it's a true solution because the particles in it may be so fine, but shining a light through it will illuminate everything. Okay, yeah, I know, I'm funny. So here, so this is a true solution, and then this would be not a true solution, a colloid. A very good example of Tyndall effect is fog. And if you've ever driven in fog, it's kind of very interesting. You can actually see your headlights, okay? Another way of seeing Tyndall effect is in your home. So when you're sitting in your home and you have sun rays coming through the window and suddenly you can see all the dust particles. No, not all your homes have dust particles, but if you can see those, that's Tyndall effect. Proteins form colloids in water. So for example, eggs, that's a protein. And then coagulation is a process where you can aggregate the colloid. Okay, so coagulation is a very interesting process. It happens all the time, and this is also a very good way of precipitating proteins out in case you're working with a colloid. So for example, curdled milk. Okay, and this is a very good way of making cheese. So you add vinegar or whatever lemon juice to milk, and you can precipitate all the protein out, and that is called coagulation. Okay, and the same thing will happen if you have eggs, for example, and you take an egg, which the egg white looks like a colloid, but of course once you boil it, you've coagulated it, which means that now it is a solid. It's precipitated out. You can add coagulating agents, you can use heat, things like that. That you will study a lot more when you get to biochemistry. And then one more thing about solutions is micelles or micelles, whichever. Micelles are formed when you have a molecule that has both a hydrophilic, which is a water-loving, and a hydrophobic, water-fearing component, okay? And this results in like really long chain of non-polar thing, which is hydrophobic, and something of an ionic thing at the end, which is then the water-loving hydrophilic part, okay? And this example that I've shown you here of sodium stearate is actually of soap, okay? And what happens with soap particles is that you have this long chain which is non-polar. If you just look at this chain without this ion present over here, you would think that the intermolecular forces here are only dispersion forces. But when you look at this portion over here, you're thinking, oh, this is an ion. It should have ion dipole forces. So, and that is the property that soap uses to mix with water, because water is supposed to have only hydrogen bonding and dipole-dipole forces. So if you mix only the left-hand side of the molecule in water, it is not going to dissolve because this is all dispersion forces. However, as soon as you have this little portion in there, along with this long chain, suddenly now this is going to be soluble in water because now the ionic forces also are going to take place. So here is what happens in water, okay, is that this is where you have the soap solution. And in the soap solution, this what happens is that the chains that you have, these long chains, they will be inside and the ions will be outside. And what they do is kind of like an aggregation thing, okay? And in an aggregation thing, this is where all the non-polar parts will come into the center and all the polar parts or the polar heads will go outside towards the water because that is what is attracted to water. This non-polar chain is not attracted to water, so it will kind of stay within itself. And remember, we were talking about adhesion and cohesion. So this is like a cohesion thing, but this portion here is like an adhesion thing. Okay, so there's both things going on over here, adhesion and cohesion. And this micelle, which is called a micelle, but in layman terms, in our general terms, we call it a bubble. And this kind of a bubble forms then, okay? And so what happens in case of soap is this right here, classic example. So if you have oil and water, which are not soluble in each other, okay? Because vegetable oil would only be this portion um, of, of a chain, and then water of course is H2O, and they don't dissolve because there's nothing alike amongst them. But as soon as you put a little bit of soap in them, it ends up mixing everything. Why? Because it ends up forming an emulsion. Why? Because these non-polar chains will start dissolving the vegetable oil, whereas the polar ends will start dissolving in water. So now you have something that can dissolve both the non-polar as well as polar substance, which is what we need soap for. It's very good for cleaning agent because what you're trying to clean is greasy, but water will not dissolve greasy stuff because it's not soluble in it. So you would need soap, okay, in order to dissolve the greasy part of it, and you will need the polar parts for something to dissolve in water because water is the cheapest solvent out there. So we'll talk more about this in class also if you want to, but this is really how micelles work. And by the way, just to kind of make a connection here for you, soap is also very good in breaking the surface tension. Okay, remember we talked about surface tension and how surface tension is caused by intermolecular forces. So as soon as you put the soap in the water, it kind of tends to break the surface tension here and dissolve both of these substances. Okay, and the surface tension breaks because you have both a polar end as well as a non-polar part. Okay, and so it really, when you start talking about micelles and colloids, we're talking about like a bigger picture here, okay, encompassing everything that we've learned about solutions and um, intermolecular forces. So your key concepts for this presentation, you need to know about solutions, of course. You need to know the Raoult's law. You need to be able to do calculations using the freezing point depression, boiling point elevation, osmosis, colloids. You should know about those things. I may not ask you very specific things about colloids, but osmosis, yes, sure. Okay, I will. I'll give you the formula. You should be able to do the calculations yourself. So again, calculating molar mass of substances, calculating the new boiling point and freezing point of substances, that is what you will have to do using Raoult's law for me.